Okay. Let me share. Hold on. Stop sharing. Let me open first my notes. Okay. Signal, digital transmission, analog transmission. Okay, and then chapter week 3 is telephone and cable network. Oh, that one will be okay. I'll upload that one later. So this one, this week we will have subject 2. Hold on. Okay, please look at the week 2. Week 2. And 1-5. I'll try to make sure that we can cover this, inshallah. Okay, let me share. So this is for week 2. That I would cover. Okay, so signals. Signals. Based on this implementation, data, signals, and transmissions mode. Okay, so for this week, I will cover about layer 1 topics. Okay, so one of them is the signals. Okay, signals from the media, from the cables, wireless, and everything else. So we need to introduce analog signal, digital signal, transmission impairment, and also the performance. So to be transmitted, the data must be transformed to electromagnetic signals. Okay, so here it means that depends on the media. Okay, so the signal should be able to be transferable, okay, based on that media. So the signals can be analog or digital, and if it's an analog, it can have an infinite number of values in a range. So the example A here shows this is what it looks like for analog signals. And for the digital signals, they have a limited number of values. To represent the digital signals, okay? So in data communication, we commonly use periodic analog signals and a periodic digital signals. So analog signals can be single and composite. Okay, so for a single signal, we use sine wave as a fundamental form of a periodic analog signal. Okay, so the sine wave of a single analog signal use this A sine, okay, 2 pi ft plus sigma. So this is how they calculate the periodic analog signals. So and then the signal can be represented by using amplitude. So what is amplitude or peak amplitude is that it's the absolute value of the highest value on the signals, okay, which proportional to the energy. So in this example, the amplitudes can be represented using a volt as an electric signals. Okay, so the highest volt is what we consider as the amplitude, okay, which is measured in volt. And then another components is frequency and period. Frequency and period are inverses of each other. So what is frequency is that it's a rate of change with respect to time. Most of the time, frequency is used on a lot of measurement and signal processing. And also in computer performance. Okay. So the frequency change in a short span of time means that it have a high frequency. So in this case, okay, high frequency does looks like, oh, erase this first. Okay. Now, high frequency is something like that's like your heartbeat. Your heartbeat is very fast, right? If it's a heartbeat that is very fast, So it's a very narrow signals. Okay, so this shows that a very high frequency, because in 1 second how many cycles that has passed through. But if it's a low frequency, it's like a slow motions. Okay, within 1 seconds. So how many frequencies? Okay, how what is the frequencies? It's based on the cycle of the wave. This one, eh? So this one is the lower part here is the low frequency. The upper one here is a high frequency. Next, so if a signal does not change at all, its frequency is zero. Okay, regardless if it's an amplitude of 5, for example, there's a 5 here and then there's a straight line there. So there is no changes. If the signal doesn't change, then the frequency is zero. But if a signal changes instantaneously, then its frequency is infinite. Okay, so how to measure? Because frequency and period are inverses to each other, so the formula is frequency is equal to 1 over period. Okay, how many period that we have? So here, um, 6 periods. Okay, this is this is the signal wave. Okay, in 1 second that has been measured. So in 1 second we have, okay, 1 period and then 2 period and then 3 period, 4, 5 and 6 period in 1 second. So to know your frequency is that 1 divided by how many periods in 1 second. So 1 divided by 6. Okay, sorry. No, yes. 1 divided by 6 is 6 hertz. Okay, 6 hertz. Okay, sorry. Yes, T is a period. Okay, so period is equivalent to 1 over 6 seconds. Okay, 1 over 6 is equivalent to seconds. So here means that 1 divided by 6 period. Okay, 6 period or 6 wave. Then you will get the seconds of period. So your frequency is, you count how many periods in 1 second. So you don't divide it. Okay. And then, okay, the units of periods and frequencies depends on the power. So seconds, and then you want to convert it to milliseconds. So we use 10 power of -3. If it's for microseconds, it's 10 power of -6. And then nanoseconds is power of -9. And then picoseconds is power of 12. Okay, and then inverse with the periods. Okay, periods use the seconds, right? So frequencies use hertz. Okay, it will use hertz. So hertz is the basic equivalent, basic value, basic unit. And then it can be represented into kilohertz is 10 power of 3, megahertz 10 power of 6, gigahertz is 10 power of 9, and then terahertz is 10 power of 12. Okay, and then, for example, we express a period of 100 microsecond in kiloseconds and express the corresponding frequency in kilohertz. So from microseconds to kilohertz. Okay, so to kilohertz, first is that we need to make the substitution. So microsecond to kilosecond. Okay. Sorry. Yes. So microseconds is equivalent to 100 times 10 power of -6, because micro is this one. We follow 10 power of -6. Then it is also equivalent to 100 times 10 power of -9, which is kiloseconds. Now we use the inverse relationship to find the frequency. Okay, so because we are using a kilohertz, then we need to find the kiloseconds, right? So previously we convert it to kiloseconds. So 100 microseconds is equivalent to 100 times 10 power of -6 is equivalent to 10 power of -4 seconds. And then because the frequency is inverses to the period. So T here is 10 power of negative 4. So we divide it 1 divided by 10 power of negative 4, which this is the opposite, eh? So this is on the bottom one. So then it will be converted or become 10 power of 4. Because we need to change from hertz to kilohertz, then we need to times 10 power of 3. Okay, 10's power of 3. Then power of negative 3, okay, then what will you get is 10, okay, 10 kilohertz, right? So now phase describes the position of the waveform. So let me see back again. Please excuse me. Back again. Data signal. Let me see my notes for the previous one. Hold on. This one, Okay, this one, this one, this one. Okay, this is the correct one. I'm so sorry. Okay, I'll upload this later on. I will upload this later on for the for this note, Okay, so the frequency calculation should be 100 microseconds times which is converted into seconds. So this one. The second line, okay, shouldn't be there's a times 10 power of 3 anymore. It's because of we already convert it to kilohertz. Okay, so 10 power of negative 3 is the representation for the kilohertz. Okay, now the phase describes the position of the waveform relative to the time zero. So some of the signals started not at the same position. Okay, so at the time zero, some of the signals start at 0 degrees. And then if it's a 90 degrees means that it start at the peak of amplitude. Okay, and then if it's 180 degrees, okay, it's actually at the 0, okay, half, okay, half of the signals, okay, half cycles of the signal sine wave. Okay, so in this time it's inverse to the 0 degrees. So it start from the bottom. Okay, from 0 it start to the bottom and then go back to the 0 back again, and then peak amplitude and then go back to the bottom to the 0 back again. Okay, so the phase is measured in degrees or radians. Okay, so sorry, 360 degrees is 2 pi rad. So 1 degrees is equivalent to 2 pi divided by 360 rad. This is the formula. And then 1 rad is 360 divided by 2 pi. So a phase shift of 360 corresponds to a shift of a complete period. Means 0 degree is also, it's a 360 degrees also. Okay, can be considered as 360, because if 180 degrees is considered as a cycle, then if we add another 100 degree, then we start back at the 0 back again. Okay, a phase shift of 180 degrees corresponds to a shift of 1/2 of a period, and then a phase shift of 90 degrees corresponds to a shift of a 1/4 of a period. This one, 90 degrees is a quarter cycle. What about 270? Okay, it will be 3/4 cycle. Okay, so looking at the figure 3.6, we can say that a sine wave with a phase 0 degrees starts at time 0 with a 0 amplitude. So here, it start at the 0 amplitude and then it increase, okay, and then going down until and then it increase back again. But okay, look at the B for a 90 degrees. The sine wave will start at 90 degrees with at time 0. Okay, that it will be the peak amplitude. Okay, it will be the peak amplitude. So the amplitude, and then after that, the amplitude will be decreasing. Okay, the figure C is 180 degrees. 180 degrees, okay, we start at time 0 with a 0 amplitude. And then the amplitude is decreasing. After that, it would increase back again to 0 and increase more until to the peak amplitude. So another way to look at the phase is in terms of shift or offset. So we can say that in a sine wave with a phase of 0 degree is not shifted. But if a sine wave with a phase of 90 degrees is shifted to the left by cycle. Okay, however, note that signal does not really exist before time zero. So this quarter was not considered, or it does not exist before that time zero. So C, a sine wave with a phase of 180 degrees is shifted to the left by cycle. However, note that the signal does not really exist before the time zero here. Okay, let me use the pointer. Yeah. Okay, so next. A sine wave is offset 1 over 6, okay, cycle with respect to time 0. So what is its phase in degrees and radians? You just use the previous formula, okay, cycle, okay, 1 over 6 times 360 degrees, then you will get the 60 degrees. And then 60 degrees times 2 pi divided by 360 rad. Then you will get the radians for that phase. Okay. Next is the time domain and frequency domain. As I have mentioned before, if signal doesn't change, then the frequency will be 0. But then, how do we represent it? We can use a time domain, but the much more better, okay, to represent is it's best represented in using a frequency domain. Okay, frequency domain over the amplitude, over the amplitude. So in this case, we are using amplitude 5. So because there's no signal change, so the frequency is 0. So only one line at the frequency 0, okay, that reach to the amplitude 5 volt. Okay, for example, another example, C, it's a signal with a frequency 16. So within 1 second, we have 16 cycles. So the frequency domain can be represented using the number of frequencies. So here it's a 16, and then until it is horizontal to the amplitude 5 volt. Okay, so that's how we represent. Sorry. Sorry. This is how we represent. The left side here is the time domain. The right side is the frequency domain. So one is to represent the signal with frequency. The second one is to represent the frequency domain. Composite signal. A single frequency sine wave is not useful in data communications. So if we only have one signal sine wave to convey a conversation, it would make no sense because in a line that have one signal sine wave can only produce a buzzing sound. Okay, so you imagine that it's because of our voice have different amplitude and different frequencies. So in order to make sense of the conversations, okay, we need to change one or more of its characteristics to make it useful. So when we change one or more characteristics of a single frequency signals, then it will become a composite signals that makes of many frequencies. According to Fourier analysis, any composite signal can be represented as a combination of a simple sine wave with different frequencies, phases, and amplitudes. Composite signal. A composite signal can be periodic or non-periodic. Okay. So a periodic composite signal can be decomposed into a series of simple sine wave with discrete frequencies. So the meaning of discrete means that the frequencies have integer values, 1, 2, 3, and so on. The non-periodic composite signal can be decomposed into a combination of an infinite number of simple sine wave with continuous frequencies that have real values. In our voice combinations, we use a non-periodic because we have different real values in our voices. But for a data, we can use a composite signal. Now, this is a composite periodic signal. Okay, so to represent the digital signal, like a bit one and a negative one here, okay, so we use a combination or a composite periodic signal. So this figure shows a periodic composite signal with frequency f. Okay, this type of signal is not typical of those found in data communication. We can consider it like a 3 alarm system, each with a different frequency. So the analysis of the signal can give us a good understanding on how we decompose this signal. Okay, so it can be divided into a series of a simple sine wave. However, we have tools, okay, for those who involved in engineering, in signal processing, then they have a specific hardware and software that can help decompose this signal. So we are not concerned about how it is done. We are only need to understand about these composite signals. Let me see the screen. No black screen. See all slide. Okay, pointer options, camera. I need to hide my. Hold on. Ni. However, we are only interested in the result. Okay, so but I cannot use my pointer anymore. So please, you can just read on the piece on the side. Also, this is the composition of the previous figure 3.10, and then decompose into composite signals into 3 different frequencies. The red one is frequency F. Okay, F here means 1, frequency 1. And then frequency 3F is frequency 3. And then frequency 9F with a black color. And the black line is frequency 9F. So in the frequency domain, they would represent it using these lines. Red color, F, and then 3F, and then 9F. So figure 3.11 here shows the decomposition of the above signals. So the amplitude of the sine wave with frequency F here is almost the same as the peak amplitude of the composite signal. So the peak amplitude of the composite signals of this one, okay, the highest one, the highest peak, the peak amplitude. So the peak amplitude is represented by this F, frequency F. And then the amplitude of the sine wave with frequency 3F is 1/3. Okay, 1/3 of the first one. Okay, frequency F. And then the amplitude of the sine wave with frequency 9F is 1/9. Okay, a little bit, 1/9 of the peak amplitude of frequency F. So we can say that the frequency of sine wave with frequency F is the same as the frequency of the composite signal. So we call it as a fundamental frequency or first harmonic. And then the sine wave with the frequency 3F has a frequency of 3 times the fundamental frequency. Okay, this one, the blue colored one. So we call it as the third harmonic. Okay, and then the 9F has a frequency of 9 times. Okay, why do we call it 3 times? 9 times is because of you calculate the cycle. So 1, 2, 3, 4, 5, 6, 8, 7, 8, 9. Okay, so we have 9 periods, right? So that's why 9 times, it's a 9F, frequency 9F has a frequency of 9 times the fundamental frequency. That's why we call it as the 9 harmonic. Okay, this is using, I'm referring to the frozen. So this is a time and frequency domain of a non-periodic signal. So the time domain has an infinite amplitudes, okay? But it can also be represented using a frequency domain. So the amplitude for sine wave of this frequency is on this value, okay? So here, the signals here can be created by using a microphone or telephone set, okay, when a word or two is pronounced. So that's why I'm saying this is how it looks like if you're using, if we record your voice. So in this case, the composite signal cannot be periodic, because that implies that we are repeating the same word or words with exactly the same tone. So to make it sense, meaning that the information is meaningful, so usually it will have a different words. Okay, it will not be periodic. Okay, in this case. So in a time domain representation, there are an infinite number of simple sign frequencies. This one. Okay, although the number of frequencies of human voice is infinite, but the range is limited. Okay, the range is limited. A normal human being voice frequencies is in between 0 and 4 kilohertz. Okay, so we have a voice in between 0 until 4 kilohertz. So the bandwidth, okay, the medium, okay, have a specific frequencies that it can accept it. Okay, it can accept it. So our signals that is generated, the data signal that is generated um uh is contained in a composite signal. Okay, and then if it can pass through to that medium, then that's what we call as a bandwidth. Okay, so the bandwidth shows here, follow the figure B, shows the minimum signals that it can accept it until to the maximum that it can accept it. Okay, so the difference between the highest and the lowest frequency is what we define as the bandwidth. Okay, so for a periodic signals, the bandwidth has a minimum, okay, or lowest frequencies and then to the highest frequencies. So the lowest frequency is 1000, highest frequency that it can accept is 5000. So meaning that in between 5000 to 1000, the bandwidth is 4000 hertz. Okay, also the same as the non-periodic signal. Okay, so in this case, when we transmit the signal, we must produce the composite signal that match that transmission medium. Okay, so that's sometimes we will you need to calculate what is the bandwidth. So based on the requirement, highest frequency minus lowest frequency. So that's the formula for the bandwidth. Okay, and then this is also another example. You just want to know, you were given a bandwidth of 20 hertz, then and then with the highest frequency. So just replace the formula, then you should be able to get the answers. Although you just need to draw. This time you need to draw the spectrum. This one also, yes. They ask you to draw the spectrum. So in between 900 to 100, okay, so we have 100, 300, 500, 700, and 900. Okay, so then you should show the bandwidth. Okay, also the same for this one. Okay, because draw the spectrum if the signal contains all integral frequencies. Okay, so one integer number, one frequencies. Okay, all right. So a signal has a spectrum with frequencies between 1000 and 2000 hertz. Okay, so this is a signal generated with a bandwidth of 1000 hertz. And then that a medium can pass frequencies from 3000 to 4000. So can this signal faithfully pass through this medium? As I mentioned before, the signal must be able to pass through to that medium from the frequency 3000 to 4000. But in this case, that signal that is generated is the frequencies is generated from 1000 to 2000. So in this case, it cannot pass through. Okay, it's on a different dimension. So answer is no. Although the signal can have the same bandwidth, the range does not overlap. Okay, so it must follow the frequencies of the medium. The medium can only pass the frequencies between 3000 and 4000. So let's say if you send these frequencies 1000 to 2000, what will happen is that the signals will totally lost. Okay, next is the digital signal. So the digital signals consist of a square wave, 1 to 0. So one can be regarded as a positive voltage. Okay, if it's a positive voltage, then we consider it as a bit 1. And then if it's a 0, then we can consider it as bit 0. So a digital signal sometimes doesn't have to be only two level. One is a 0 volt and then one is positive volt. Okay, for example, 5 volt. Okay, it can also have more than two levels. Okay, so on B, we have a digital signal with 4 levels because we want to send more than one bit. In this case, level 1 is negative. Okay, negative, maybe negative 10. And then level 2 is a negative 5. And then level 3 is positive 5. Level 4 is positive 10. So it can represent, each of these level can represent 2 bits each. Okay, bit rate and interval. Okay, compared to analog signals, okay, we have period and frequencies, right? Okay, on digital signal, we use bit interval, which is the time required to send one single bit. To send one single bit, we call it as a bit interval, the time required to send this one bit. But bit rate is the number of bits interval or the number of bits that we can send in 1 second. So we will express this total bits, okay, per seconds. Okay, so in this case, in 1 second, we have 8 bits have been sent out. So we can also say 8-bit intervals. So bit rate is 8 bit per second. A digital signal has a bit rate of 2000 bit per second. So what is the duration? So we reverse it. So bit interval is the inverse of the bit rate. So if we have 2000 bit per second, so 1 divided by 2000, then you will get your bit interval or the duration to send one bit. Digital signal as a composite analog signal. Let's if we have a data. Okay, if we have a data and then we need to send it out to the medium. So some of the medium cannot send through the digital signal. We must change it to the composite signal. So in this case, for a digital signals, we present it using a time domain. Okay, time domain of a periodic digital signals, just like this. So we can represent it using a composite analog signal using first harmonic, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, 11th harmonic, 13th harmonic, or maybe more. But for a non-periodic, okay, so the time domains, okay, in a digital form will be like this, but in a composite analog signals can be represented like this, okay. So for a transmission of a digital signal, how do we want to send a digital signal? Okay, one example of digital signal. Okay, for example, we want to send emails. Your emails is in a digital form, right? It will transform into a bits. Okay, so all your data in a layer 1, okay, from layer from layer 5, which is an applications to transport to network to data link layer until it reached the physical. So at the end of the physical at the end of the physical layer, it will become a binary numbers. So binary numbers is a form of digital numbers. So digital numbers here will be represented into a digital signals. So let's say you want to send these digital signals, okay, that consists of a binary numbers. So the baseband transmission, okay, would send a digital signal over a channel without changing the digital signal to an analog signals. Thus requires that we have a low pass channel, where a channel with a bandwidth that starts from zero. In this case, it's because of the digital signals can consist of a value of zero in this case. For example, the entire bandwidth of a cable connecting two computers is one single channel. So as another example, we may connect several computers to a bus, but not allow more than two stations to communicate at a time. So even though we use a bus channel, bus backbone, bus topology, the communication still use dedicated, or it only allow uh, from one PC to another PC to communicate at one time. Okay, compared to comparison between analog versus digital, the analog bandwidth of a medium is expressed in hertz. The digital bandwidth in bit per second. Digital transmission needs a low pass channel. Okay, so for a low pass channel to transmit the digital signals, and then analog transmissions can use a band pass channel. So, if you want to preserve the exact form of a non-periodic digital signal with a vertical and horizontal segments, we need to send the entire spectrum. Okay, you need to send the entire spectrum. The continuous range of frequencies between 0 and infinity. Okay, between 0 and infinity. So from 0 and then to infinity, so there's an infinite value there. So this is possible if we have a dedicated medium with an infinite bandwidth between the sender and receiver that preserves the exact amplitude of each component of the composite signal. Although this may be possible inside a computer, okay, because you have between CPU and memory. So it's possible if you can use the low pass channel, okay, but it's not possible between the two devices, okay. Internally, yes, you can use, but if you want to send it to another computers, unfortunately, it is not possible. But fortunately, the amplitudes of the frequency at the border of the bandwidth are so small that they can be ignored. Okay. Here, the border here on the left side and the right side here can be ignored. So then they can create it into a bandwidth that is supported by the medium. So this means that, let's say if we have a medium such as a coaxial or fiber optic that has a very wide bandwidth, then these two stations can communicate using digital signals with a very good accuracy. Okay, broadband transmission or modulation means changing the digital signals to analog signals for transmission. So if the medium are required an analog signals for the transmission, then we need to modulate it. You change it, digital signal to analog signal. So we call it as modulation. So modulation allows us to use a band pass channel. A band pass channel means that the bandwidth of that channel, a channel with a bandwidth that does not start from zero. Compared to the previous one, this is a low pass channel that can start from zero. So this time it cannot start from zero. So this type of channel is more available than the low pass channel. Okay, if the available channel is a band pass channel, we cannot send the digital signal directly to this band pass channel. You need to convert the digital signal to an analog signal before we can transmit it. So this is the usual practice when we try to send a digital signal through the modem, okay, through the telephone line. So the telephone line must transfer using analog signal. Okay, we need to convert it to an analog signal before we can transmit it through the telephone line. So this is the process of modulation. Okay, changing the digital signal from inside our computer. Okay, and then we convert it to analog. Okay, so where does this happen? On your network interface card. Okay, on your network interface card. So your input analog will be converted into an input analog signal here. Okay, so they have F1 until F2 signal bandwidth. So then they can create the input analog signal. After that, they would pass through to the band pass channel based on the available bandwidth. So when they convert it or they modulate it, it must match to that available bandwidth. After that, when it receive, then they convert it back this input analog signal, okay, to a digital signal. Okay, so this is the functions of your network interface card where it need to convert this analog to digital and then digital to analog. Okay, right. So data rate limit. Okay, data rate limit. So every medium has its own limitation. Okay, has its own limitation. They would be susceptible to a noise. Okay, even if you you plant the cables, okay, underground, okay, it's still susceptible to a noise. So ideally, it's a noiseless channel. If there is a noise interference, so we use the Nyquist bit rate, which is 2 times B, which is the bit rate times log L base 2. But it's not realistic. So usually they use a Shannon capacity to calculate the capacity of the noisy channel. So we use the bit rate, okay, log 1 plus signal to noise ratio, okay, and then base 2. Okay. Now for the noiseless channel, we can just calculate by the value of the bandwidth. Okay, and then we uh the bandwidth transmit a signal with a 2 signal level. So 2 signal level means a 0 can be 0 to 0 and positive 5. So here means that 2 level of signals. So log 2 base 2 times 3000 times 2. So log 2 base 2 is 1. Okay, times 3000 times 2 is 6000 bit per second. But consider the same noiseless channel here, transmitting a signal with 4 signal levels. So for each level, we send 2 bits. Okay, for 4 signal levels means that log 4 base 2. So 4 base 2 means that 2 times 2, 2 times 2. So we will get 4. So 2 bits, we send 2 bits times 3000 times 2. So then you will get the bit rate of 12,000. Okay, now consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. So if it says almost 0, then the noise is very strong and the signals is faint. You cannot hear at 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 all. So for this channel, the capacity is calculated as Shannon capacity is B log 1 plus signal ratio base 2. So B log 1 plus 0 base 2 is considered 1. So B times 0. Okay, log 2 base log 1 base 2 is 0 actually. So B times 0 is 0. And then we can also calculate the Shannon capacity or the capacity of right, a telephone line. So a telephone line normally has a bandwidth of 3000 because of our voice is in between 300 hertz to 3300. Okay, so the signal to noise ratio is usually 3162. Okay, in this case, The capacity is that 3000 log 1 plus 3162 base 2. Okay, so 3163 base 2 is equivalent to 11.62 times 3000, which you will get 34,860 bit per second. So that's where it comes. The bandwidth of telephone lines in for the voice that can be accepted, or the maximum is 34. The data rate that can be transmitted is 34 kilobit per second for a telephone line. Okay. Okay, this is for another example for the 1 megahertz bandwidth. Okay, next is the transmission impairment. Okay, there's no perfect medium, okay, that can satisfy the requirement of a data communication channel. Okay, because they are factors that affect it. For example, attenuation, there's a distortion, there's a noise. Okay, that will affect the signals transmitted on that medium. Okay, what is attenuation? It's a loss of energy. Okay, your amplitude, the amplitude is dependent on the energy level. Okay, the volt. Okay, so at point 1, this is the original signals. And then when it reached to point 2, it is attenuated. Okay, because it's affected by the noise, the distance. Okay, so you can imagine if it's too long, if how much the energy needed to transfer or to run for a short distance and for a longer distance. So if it's a longer distance, you would not have energy anymore. Okay, so that's how does it look like for the signal also. So at one point, if it's attenuated, it will be amplified. Okay, it will need to go through to the amplifier so that when it reaches to the next point, it will be amplified. Okay, so the formula used is that the power signal, okay, the power signal from point 2 divided by point 1. Okay, power signal for point 2 divided by point 1 log base 10. Okay, log base 10. So log base 10 multiply by 10. Okay, so that's the formula for the signals travel. So imagine the signal travel through a transmission medium and its power is reduced to half. So from point 1 to point 2, the power is reduced to half. So in this case, P2 is equal to half P1. So in this case, the attenuation can be calculated by 10 log P2 divided by P1 base 10. So we replace P2 to 0.5 P1, then you will get the answer 0.5. So log 0.5 base 10, it's a negative 0.3 multiplied by 10, you will get negative 3 decibel. Okay, so signals is signal unit is in the decimal, decibel. Imagine a signal travels through an amplifier and then it increased 10 times. Then this time P2 is equivalent to 10 P1. So when 10 P1 divided by P1, then you will get 10. Okay, so log base 10 is equivalent to 1. So 1 times 10 is 10 decibel. So this is the value of the amplification. Next is the distortion. Hold on. Right. Distortion is a signal changes its form or shape. So from a composite signal, like the original one, when it is transmitted, okay, when it is transmitted, it consists of different frequencies, right? So different frequencies have different speed. Okay, they have a different speed. So when they reach to the destinations, the components is out of phase because they have a different speed. Okay, when they reach to the point. Some of them will reach earlier, some of them will reach later. So when they combine it to become a composite signal, it distort, it change it from the original one. Okay, and then another one is the noise. Type of noise such as thermal noise, induced noise, crosstalk, and impulse noise. So noise here would affect the signal. Okay, to the point it would change the amplitude or the frequencies. No, not the frequencies, but the amplitude. So it would represent into a different type of data. Okay, so the type of noise that can affect the signals is thermal, induced noise, crosstalk means that there's a multiple cables or mediums that is having a conversations, and then impulse noise. This one, throughput, it's a performance factor, a performance value. So throughput is a measurement of how fast data can pass through an entity. So let's say we have a bunch or a sizable of bits that pass through a transmission medium. Okay, like this is like an imaginary wall. So the throughput is that the number of bits passing through this wall in a second. So in 1 second, how long does it take? Okay, to pass through this that wall in 1 second. Okay, so that's the throughput. Whereas the propagation is the measurement of the distance, a signal or a bit can travel through a medium in 1 second. So the propagation time is measured from T2 to T1. Okay, so when they measure it, they measure through two different times. Then they calculate the distance. Okay, they calculate the distance. We divide it to T2 minus T1. So that is the propagation time. Okay. So that is for the lecture 2, data signal and transmission mode. Okay, that is covered for digital signal. For this one, I compress it. I compress it to become like this. Mana ni? 1 and 1/6. This one. Okay, digital. Only this part. Okay, not analog transmission is not done yet. For the digital transmission, okay, so this one for the what I have covered is only one part, right? For the data signal and transmission mode. Okay, so now for the coding for the digital signal, how do we convert it? How do we convert it? Okay, let me make it smaller. Okay, hold on. Okay, so this is for the signals, right? So next is that, okay, digital signals. Okay, digital signals transmission. Okay, let me stop this. Stop sharing. Okay. No, stop the escape. Okay. Okay, let me share back again my notes for the digital transmission. Okay. Okay, for digital transmission, we have digital to digital and then analog to digital, because sometimes your data is can be an analog. Okay, can be an analog, so we need to convert it to digital also. Okay, so for digital conversion, we can use line coding and block coding. Okay, and some of them would use both to convert. So, sorry, my mistake. For digital signal, digital to digital conversion, we need to use both, line coding and block coding. Okay. So what is a line coding? It's a process of converting a binary data a sequence of bits to digital signals. Okay, so this digital data need to be encoded to become a digital signals. Data in sorry. Data is in the form of text, numbers, graphical images, any audio or video, which will be stored in the computer memory. So if it's in a computer memory, then it is it's a digital data. Okay, as a sequence bits. Okay, because it stored in a sequence bit. So this digital data will pass through to the encoder, where this encoder would transform it, convert it into a digital signals using line coding, okay, and then block coding, okay, and then send it back to the decoder. We encode it back to become digital data so that the receiver can process it. Ish. Okay. Now, what are the characteristics of line coding? Okay, so we need to consider signal level, data level, data rate versus signal rate, bandwidth, baseline wandering, DC components, and self-synchronization. Now, a signal level compared to the data level. So, for one signals, okay, they can be represented by one data element. So, look at the figure A here. These signals, okay, signal level versus data level. Here, figure A represent that one data element per one signal. Okay, per one signal. So, one signal element means that R is equal to 1. Okay, R is equal to 1. But if we use two signal element, this one is one signal element because only one level. Okay, so for bit 0 is represented on a positive value, and then bit 1 is represented as a negative voltage. Okay, one data element. Now, for figure B here, as you can see, we have two level. One is a negative one and then one is a positive one. Just to represent one data element. So in this case, one data element per, okay, per two signal levels. Then R is equal to 1 over 2. Okay, 1/2 lah. A half. And then for a signal element, for example, if it's a positive or a negative, then it can represent to two data elements in this case. So here we can say that two data elements 0, 0, 0, 1, 1, 0, 1, 1. So two data elements, okay, data elements or 2 bits here can be represented per one signal element. So R is equal to 2. Okay, R is equal to 2. And then some of the signal elements, okay, signal elements here, one is the highest voltage, and then 0 voltage and negative voltage. So in this case, each of these signal elements represent 4 bits. Okay, 4 bits data. So 4 bits data, in this case, 4 data elements. Follow the arrow. Okay, the scope. The scope of the 4 data element is from these 3 signal elements. Okay, so 4 data elements per 3 signal elements means that R is equal to 4 divided by 3. Okay, so what is data rate? Number of bits or number of data elements sent in 1 second, which is a bit rate. Okay, and the signal rate is number of signal element sent in 1 second, also known as a pulse rate, modulation rate, and baud rate. Okay, so signal rate can be calculated by C times N times 1 divided by R. Okay, C here is the case factor, N is the data rate, R is the previously defined factor. Okay, so a signal is carrying data in which data element is encoded as one signal element. Okay, so if the bit rate is 100 kilobit per second, what is the average value of the baud rate if C is in between 0 and 1? So if it's in between 0 and 1, the average value is 1 divided by 2. It's because of in between. So in between, then we can consider half. So 1 divided by 2. So the baud rate, okay, the signal rate or the baud rate here is C times N. Okay, N here is 100 kilobit per second. So we convert it to become 100,000 bit per second. Okay, and then times 1 divided by R. What is our signal element? R is equal to 1. So 1 divided by 1 is 1 times 100,000 times C here is the average value, the carrying data, so case factor. So the case factor here is based on the carrying data here. The average value of the baud rate also in between is 0 and 1, so half. So 0.5 times 100,000, it's 50,000. We put a value of baud, so 50K baud. Okay. Direct current component. Signal pass through a system that not allow the passage of a DC component. If it doesn't allow the DC component, you should be able to see that there's no negative amplitude, okay, negative volt, okay. But if that signal, a signal doesn't allow that a signal without the DC component, okay, a signal that has no DC component, then it can be represented, the voltage or the amplitude can be represented using a negative volt. Okay, so to ensure that receiver's interval must correspond exactly to the sender bit's interval, they must have some self-synchronization. Here, this is the sender that has been sent out. The data that has been sent out should be like the original one. But when it reached to the receiver, sometimes the receiver has a different speed. They have a different speed. So what they can presume, what they can perceive from the data or what they translate it will be different value. Here you can see this one should be 1011. But instead, because the signal is having a different period, right? The intervals. So it was considered as bit 110111 like that. Okay, so now they understand it in a different data. Okay, so the information has been changed. So in between the network interface card of the sender and receiver, they must confirm or they must able to identify the speed. If the speed is too fast, then they need to ensure that put a stop bits or maybe put a gap or slow down. Okay, slow down its speed of sending out or maybe slow down its processing. Okay, so there's some self-synchronization in between these two network devices. Okay, so imagine that if we don't have a self-synchronization. So in a digital transmission, the receiver clock is a 0.1% faster than the sender clock. Okay, so how many extra bits per second does the receiver receive? If the data rate is 1 kilobit per second. So how many data if the data rate is 1 megabit per second? So at 1 kilobit per second, because they have 0.1% faster, so 0.1 times 1000, you will get 1 bit extra bit, right? 1 bit extra bit. So 1 bit extra is the value of the extra bits that is received. Okay. So it's because of the receiver is 0.1% faster. So you calculate 1000 times 1.1. So you should get 1001 bits, which is the 1 extra bit per second. However, if we have, if it's only 1 extra bit, still can be relatable. But what about 1 megabit per second? So 1 megabit per second means 1 million. So if it's a 1 million times 1.1, so what would you get is that 1,000,000 bits received. If we calculate the differences, you will get 1,000 extra bit per second, which is detrimental. You change it, you change a lot of information. Okay, we will assume a different information that is sent out. So that's why self-synchronization is very important. Okay, and also the type of line coding scheme that is used, okay, will determine uh, the the receiver, okay, the receiver of the receiver processing. Okay, another one is the direct current component. If it doesn't allow the passage of DC component, then a signal with a DC component can only allow this positive voltage only. Yeah. Okay. Now, for line coding scheme, we have unipolar, polar, bipolar, multi-level, and multi-transition. I'm not sure if you are covered. Some of you, that is UTEM graduates. Yes, you must have come across on this part: unipolar, polar, bipolar a little bit, and then multi-level is only introduction, and then this is a multi-transition. Okay, so MLT3. So I think I have covered a little bit part of that. So unipolar encoding is a very simple and primitive that only use only one voltage level. So 1 and 0 is represented using a positive and 0 voltage. However, and then but this, okay, could not represent or have a problem with the DC here, DC flow. Okay, and also for the self synchronization, because of if there's a change of speed happen, we would not know if this speed is 0 or not. Okay. And then polar encoding uses two voltage level using a positive and negative. Okay, NRZ, RZ, Manchester, and differential Manchester. So the NRZL is the level of the signal. Here, L here, the level of the signal is dependent upon the state of the bit. 0 is considered positive, L is considered negative. Okay, so the transition is based on the state of bits. And then for the NRZI, I means invert. So signal is inverted if a 1 is encountered. Okay, so if 1 is encountered, in this case 0 is positive, but if it's encounter 1, it would reverse the signal from positive to a negative. And then 0 means we retain the state. So 0 here means that it's still in a negative voltage, and then still 0, still negative, and then the next one is a 1. So they change the edges. Okay, the signal is inverted from negative to positive. So this is NRZI. Okay, and then RZ encoding. RZ encoding, the signal change during each bit. Okay, in between, they change the signal. Okay, to ensure that when the receiver receive it, they can determine the self synchronization. Okay, the self synchronization, but the DC could not be maintained. Okay, so some of them have if you read it, okay, if you read on the textbook, okay, they have certain advantages and disadvantage for each of this encoding. But the RZ here can maintain the synchronization. So now, if it's a 0, okay, it will transition. Okay, it will transition, okay, to a different state, and then to a 0, to a 0 here. Okay, now if it's 1, okay, it will go to the top and then change, okay, and to this change the state, Okay, from positive to 0. Okay, if it's a 0, okay, it would transition. Okay, it would transition. Okay, 0 is a negative voltage. So for a negative voltage, it will go down. Okay, start at negative and then pass through. Okay, and transition back again to 0. Okay, and then when a 0 again, they use the same pattern. They will use the same pattern. Okay, and then when 1, so from 0, go up to the edges, and then from the positive, they change the signals, okay, and in the middle, and then go to the 0. Okay, so this is return 0. RZ means return 0. So for each of the signal, regardless, one is a positive. So from the peak amplitude, they would return to 0. If it's a bit 0, if it's it will be from the negative, return to 0 also. Okay. Manchester encoding. Manchester encoding also use a transition at the middle of the bit that is used for self-synchronization, to synchronize the bit and when they reach to the destination. So, and also it can be used for a bit representation. 0 is like a Z, and then 1 is like opposite of the Z. So 0 here is like this, and then they will continue if it's 1. But if it's a 0 and 0, as you can see, it must use the same pattern. So they would go up the edges. Okay, go up to the edges because they want to start at the positive voltage. Now, differential Manchester encoding. The transition at the middle is used only for synchronization. But the bit representation is defined by the inversion or non-inversion at the beginning of the bit. Okay, at the beginning of the bit would determine the inversion or not. So differential here, okay, if the bit start at 0, so assuming that it start at the positive 1, okay, so it will go down. Okay, it would transition. Okay, it would transition. So the presence of transition at the beginning of the bit would means that it is a bit 0. Okay, but if there is no transition, then it's a bit 1. So in this case, if it's a bit 0, so let's say we are from the positive, we go down, and then we transition in the middle, okay, for synchronization, and then go up. But bit 1, okay, doesn't inverse. It's not inverse. Okay, it's not in the state of inverse. So to tell you that is bit 1. So they would, okay, continue, and then transition in the middle and go to the bottom. And then next is a bit 0. So because it's a bit 0, then we change the direction. Okay, we change the direction. So from the bottom or from the negative to positive, and then cross in the middle, okay, straight to the middle, and then transition back again. So this time it's at the bottom again. So the next bit is also 0, then we continue. So this is what we call as differential Manchester encoding. Okay, what about bipolar? In bipolar, they use the 3 levels: positive, 0, and negative. One here can be used to represent using a positive and negative alternatively. So in this case, first they start, if there's a bit 1, we start at positive. Then the next bit, it will become negative. If the next bit is bit 1, again, repeat back again. Positive, negative, positive, negative. Okay. Sorry. Okay, next. Multi-level. Okay. 2B1Q for ADSL. This most of the usage of the ADSL modems. They used to be 1Q. Okay, some of them. So 2B1Q means that 2 binary, 1 quarter. Okay, so it uses 4 volt level. This is an example they use, positive 3, positive 1, negative 1, and then negative 3. So, for representation of to transition. Okay, to transition to the next level. Okay, so if the previous level is positive, then the next level, it will become plus 1. But if it's a previous level is negative, this one, then if it's the next level, if it's the next level, then we follow the positive one, positive 3, like that. Okay, so bit 0. Bit 0 start at negative. Okay, in this case, bit 0 start at negative. So the next level is 1, 1. Okay, the next level is 1, 1. So we follow the negative here. So 1, 1 means 1, 1 here means positive 3. Here, positive, positive 1, positive 1. So 1, 1 here, it's a little bit different. So, the example here, should be different. Okay, so it should refers to the level here. Okay. Okay, so if the next bit is 1, 1, okay, if the next bit 1, 1, if the previous level is negative, then it should be positive 3. So it should be at the top, this one. Okay, it should be at the top. So you read it based on this previous level, and if it's a positive or negative. Okay, and then what is the next bit? Okay, what is the next bit? So if the next bit is 0, 1, okay, the next bit is 0, 1, which is positive 3, like that. Okay, let me draw back again. Okay. Okay. Now, okay. Now, this is positive 3, and then this is a positive 1. Okay. Let me make it smaller. Like this, So positive 3, positive 1, and then negative 1, and then negative 3. Okay, so this is our time. Okay, and then okay, so this is your amplitude, So now, so if it start at 0, 0, which is from negative, okay, from negative. So it should be, if it start from negative previous level, which is the next one should be 1, 1, right? So 1, 1. Okay, so if the next bit is 1, 1, and the previous level is negative, it should go up to the positive 3, like this. Okay, next. 0, 1. So next is 0, 1. I'll write it first. So 0, 1, 1, 0, and then 0, 1. Okay, 0, 1, like that. Okay, now, the next bit is 0, 1. And it is a positive. Okay, so if it's a positive, the next symbol is a positive, then we need to maintain the positive 3. Okay, and then, if its next is 1, 0. 1, 0, previous level is positive, 1, 0, previous level is positive, then it should be negative 1. Okay, then next this one. And then, okay, next is 0, 1. 0, 1 is previously it's a negative, right? So previously it's negative, then it should go to negative 3. Then we follow this one, like this. Okay, So we follow like this. Okay. Now, this is what it's look like for a multi-level. They based on transition table. Okay. Now, for MLT, it's a multi-line transmission. So the multi-line transmission uses 3 levels of signals if it's a positive one, 0, and negative one. Okay, for the voltage. So it uses a transition states. Let's say starting is 0, starting at 0. So if the next bit is 1, so if it starts 0, next bit is 1. So we go down. Next bit is 1. Last is non-zero. Next bit is 0. Next bit is 1. Okay. So if it's a last non-zero, it's a negative or positive, then it will go to positive. Okay. So it will go to the positive first. And then, okay, now, next is 0. If the next bit is 0, then it will maintain the positive 1. Okay? And then, if it's a next bit is 1, it will go to 0. So, here the value, okay, becomes 0 volt. Okay, so if the next bit is 1, and then the previous value is non-zero, it's a positive V, okay, means positive voltage, because previously it's a positive, then it will go to the negative voltage. So here, the next one would become a negative voltage. So the next is bit is 0, so it will maintain the state. So it will become 0 volt, negative volt again. And then the next bit will become 1. So it goes to the voltage 0. And then if the next bit is 1, okay, next bit is 1, then it will follow the last non-zero. It will follow the last non-zero. So the last non-zero is negative. So it will become positive. Okay, this one will become a positive. So this is a multi-line transmission. Okay, once we have converted into a line coding, then okay, all these all the data, the digital data need to be converted into a block coding. So they would divide it into MB divisions, means M bits. Each of these digital data becomes an M bits, and then they would do some substitution, okay, to become an N bits, Then we convert it to using to become a digital signal using a line coding. So line coding depends on the line on the transmission, the network interface cards and the transmission media that is used. Okay. So what is a substitution in block coding? Here, this one, okay. When we divide it into M bits, for example, this one we use 4 bits. Originally, this is a M bit of 4 bits. So 4 bits is substituted into a 5 bits block. Okay, so 000 become 11110, and then 001 becomes 01001. So there's some calculations encoding that is used. So example is that they use 4B over 5B. So 4B to 5B code encoding, they have some table. 000 is referred to this one, 11110. And then 001 will become 01001. So all data, 4 bits data can be represented from 0 to 15, can be represented into 5B encoding. Okay, let's say you want to differentiate to a quiet signals, idle, halt, start delimiter, end delimiter, then because we have 5 bits, because we use 5 bits, then we have an extra bits. These extra bits is to use to represent other type of data such as quiet, idle, halt, start delimiter J, K, T, set, and reset. Okay, so this is like a signals to tell Okay, it's a set. It's a reset. Okay. And then let's say our data is in an analog. So you need to convert it to digital conversion. So we need to use pulse code modulation. Okay, pulse code modulation must go through three processes. So let's say this is your analog signals. It will be encoded in the pulse code modulation. First, we sample it. Okay, you sample it, and then it would produce into a pump signal. Okay, so your analog signal would be quantized. Okay, it would be represented using a pump signal. Okay, just like this. Okay, it does similar to the analog signal, right? Because this is like a time domain frequencies, time domain frequencies, and then we quantizing it. When you quantize means that you give a value. Positive 53, positive 99, positive 120. If it's a negative, negative, something, 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 something. Now, then this positive value or negative value would be encoded into a digital data. Like you encode positive number into binary numbers. If it's a positive, then it should be 0 at the front as the signals, and then if it's a negative, then you will use 1 to encode it. Okay, my mistake. Sorry. So this is the process of the sampling. The analog signal is sampled every every period, where the period is the sample interval or period, also known as a pulse amplitude modulation. Okay, so for a certain period, this is the pump signal that has been sampled out, and then after that, they would sample the analog signal to become um a flat top sampling, okay, to get a digital value. Okay, to get the digital value. So A is the ideal sampling, B is the natural sampling. They get divide it, okay, to become to get a block, okay, a block sampling. And then after that, flat top sampling. Okay, then we quantize it. We quantize it to become a value. I'm aware that we reached to the 9 o'clock, but I just want to make sure we can finish until day 15. Okay, and then so this is the quantized pump signal. After that, this quantized one would be represented by using a sign and magnitude of a binary numbers. The one that you have learned during the computer organization and architecture. So you represent it using the sign bit. 0 is positive, 1 is a negative number. Okay, by using this, then you can represent this quantized signal. Okay, so positive 24 is 0001100, something like that. And then we transfer it by bit. Okay, and then okay, now we go through to the process. So analog data comes through to the modulation of pump signals. So this is the pump signals, and then going through the quantization so that we get the value of the integral value of the quantized data. And then we encode it using a binary data. And then once we have this binary data, then we can convert this using the line encoding. Either we want to use a multi-level or bipolar AMI, depends. Okay. Now, once we convert it into line coding, then we can send out through the medium. Okay, so then it will become a digital signal. Okay, so according to the Nyquist theorem, the sampling rate must be at least 2 times the highest frequency. Okay, so the highest frequency is X hertz, then the sampling rate that we derive from it must be increased. They must increase it, so 2 times samples per second. Okay, so the sampling interval is equivalent to half of the hertz. So note that we can always change a band pass signal to a low pass signal before sampling. So in this case, the sampling rate is twice the bandwidth. Right? So the calculation for a sampling rate depends on the bandwidth. Okay, for a signal with a bandwidth of 10,000, bandwidth from 1,000 to 11,000 hertz. So the sampling rate should be two times, twice the highest frequency. So it should be the highest frequency is 11,000. So two times 11,000. So your sampling rate should be 22,000 sample per second. Okay, a signal is sampled, and then each sample requires at least 12 levels of precision. Means positive 0 to positive 5, and then negative 0 to negative 5. So how many bits should be sent for each sample? Okay, we need to send, we need 4 bits. Okay, 1 bit for the sign, positive here, and then 3 bits for the value. Okay, because of 5 can be converted into binary 101. Okay, so a 3-bit value can represent 2 power of 3, which is equivalent to 8 levels from 000 until 1111. So which is more than what we need. So a 2-bit value is not enough since 2 power of 2 is equal to 4. Cannot we cannot represent until 5, right? So a 4-bit value is too much because 2 power of 4 is considered is equivalent to 16, whereas we only need from 5, okay, from 0 to 5 to represent the value. Okay, and then we want to digitize the human voice. So what will be the bit rate? So human voice contains frequency from 0 to 4,000. Okay, in general. So sampling rate is 4,000 times 2 of the sampling rate or over seconds. So bit rate would be sampling rate times number of bits per sample. So 8,000 times 8. Okay, assuming 8 bits per sample. So 8 bits per sample. So 8,000 times 8. Okay, you will get 64,000 bit per second as the bit rate. Or in kilobits, 64 kilobits per second. Okay, so that's all for the digital transmission. Oi, 31 pages, Okay, oh, there's a lot of exercises. Okay, um, I would just elaborate it in general, okay, because this has been covered on the data communications in degree actually. So I'll just continue with the analog transmission. So under the analog transmission, we would modulate from the digital data to analog, okay, by using a certain modulation method technique, okay, ESK, FSK, PSK, QAM, and then bit or baud comparison. Also, we also need to modulate from analog data to analog signal by using amplitude modulation, frequency modulation, and phase modulation. So for digital to analog conversions, it's the changing of one of the characteristic of the analog signals based on the information in the digital signal. So we need to use modulator and demodulator. So 4 types. Okay, the most basic is 3 types. Okay, amplitude ASK, amplitude shift keying, and the frequency shift keying and phase shift keying. And then there's an improvisation. Sorry. The combination, a hybrid technique that combine amplitude and phase. So the name is that's the name as QAM, quadrature amplitude modulation. So as usual, bit rate, baud rate has been covered. Now, the example is that we want to find the bit rate. So this is another formula that we can use. If we have the bit rate and we can also calculate the element signals, signal elements. Okay, so in this case, signal elements is 4 bits per signal element. So R is equal to 4. So you can calculate by S. Okay, S is the signals rate. Okay, signal element, sorry, signal elements per second. So 1000 is sent per second times 4 bits per signal element. So you will get 4000 bits per second. Okay, so amplitude. So what are the attribute that they use? Depends. They would depends. The name itself will show you. So amplitude means that the amplitude will be different. The rest, phase and frequency would be constant. So in this case, baud rate and bit rate would be equal. The value will be equal. So for the amplitude to represent one, they use a different amplitude. One is a different one amplitude, highest amplitude, and then zero is zero amplitude. Okay, so to represent this value, in 1 second, it can send one signal element. So the bit rate is 5, the baud rate is also 5. Okay, so the calculation is the same. If your baud rate is 5000, then your bit rate is also 5000. What about frequency shift keying? Means that the frequency would change, would be varied. The rest will be the same. Also, the calculation for baud rate and bit rate is the same. So, look at the differences between the frequency for bit 0 and bit 1. So, in this case, for bit 0, the frequency will be lower. And then for the bit 1, the frequency will be higher. Okay. And then phase shift key. Phase shift key means that the phase would change. So the frequency and amplitude would remain constant. And PSK also, if the bit rate is 5, then the baud rate is also 5. So S is equal to N. So in this case, look at the phase, the degree of the signals. For bit 1, degree 0. For bit 0, degree is 180 degrees. Okay. And then um the the disadvantage of using amplitude, frequency and phase is that the value can be affected by the noise. Okay, so and then what will happen if the synchronization fail? So the value would change. Okay, in this case, for the phase shift keying, it will not start at 180 degrees. It will be different. So what they do is that they combine. Okay, they combine the features, two features. In this case, ESK and PSK, so that the maximum contrast between each signal bit is achieved. And also, they can send a different level of data. Okay, so that for each of these signal level, it can carry more bits. So here, phase and amplitude of the carrier is varied, but the frequency can remain the same. Okay, so the only drawback is that if the speed on the other end is faster, then they need to have some self synchronization. So here, for QAM, they combine the phase and amplitude. So for bit 000, they would use lower amplitude and 0 degree. And then 001, where is it? 011? 011 use a higher amplitude and also 0 degrees. So how do they represent this using this type of different phase and amplitude? We look at they use a QAM bit point. Okay, QAM bit point. Here, okay, now I change it there using this one. Okay, for a bit 000, so bit 00, let me write it like this. Okay, so bit 00 start at 0 degree. Okay, 0 degree and lower vote. Okay, lower vote here is like 5, eh? So I'll use a lower vote. So this is the point for bit 000. Okay, so this will be 001. Okay, sorry, 000. Okay, 000. And then about 001. 001 will use a higher amplitude, but still 0 degrees. So 001, like that. And then 010. 010 use 90 degrees. Okay, they would use a 90 degrees. And then low amplitude, and they would use a low amplitude. So if it's a 90 degrees, then low amplitude, then this is the position of 010, like that. And then the next continues. So there's a point here. This one, this one, this one. Sorry. Not this one. This one, eh? And then the bottom one. Okay, so also this one side. Okay, you should be able to see that there's an 8-bit here. Okay, not this one, eh? So let me cancel back again. Kenapa tak boleh? Hold on. Okay, change it. This one, this one, this one. Okay, so okay, for 1111. Here, this one, eh? So this one use a 270. Okay, 270. And then the lowest, okay, the lowest amplitude. So it should be here. So 1111. So 1111. So that's the position that you use. And then for 1110, so still 270 degrees here. Okay. Okay, and then 1110. So 110. And then 101. So 101 start from negative, eh? So negative for here. So 101. Okay. And then sorry, this is 101. 101. And then this one should be 100. Okay, 100 should be here. Okay. So sorry. This one should be 2,000. Okay, 200 and 100 is 180 degrees, right? So it should be half. So if it's half, it start from here, from this side. Okay, and then this side. Okay, so another is for 90 degrees here. And then another is 90 degrees there. Okay, so that is they use like a quadrature amplitude modulation table to map, okay, to refer and then convert it using these signals. Okay, now modulation of the analog data is using an analog to analog conversions. So from a composite signals, it becomes like an analog signals here. So they use an amplitude modulation or frequency modulation or phase modulation. So this is like the original modulating signals. And then we convert it, okay, we modulate it with the carrier frequency. So the frequency and phase of the carrier will remain the same, only the amplitude changes to follow the variations of this modulating signal. Okay, so the frequency and phase is the same, only the amplitude changes to reflect the signal. So then how do we modulate it? We can use the AM bandwidth. Okay, the AM bandwidth using the amplitude modulation. So using this amplitude modulation, they amplitude it, they modulate it based on the frequency of the carrier here. Okay. Each of the AM, okay, has been allocated, okay, with a certain size, okay, of band allocation. So the bandwidth for each of the band will be the same, okay, for to represent or to provide uh the the station, the one that produce the signals. In this case, it's like the radio frequency signals, right? They have the band allocation. So for each band, they have a certain bandwidth. So for one band here, they would be assigned with 10 kilohertz to represent that station. Okay. And then if we are using a frequency modulation, so the frequency modulation like your radio, okay, use a frequency modulation. So the frequency of the carrier signal is modulated to follow the changing amplitude of the modulating signal. The peak amplitude and phase of the carrier signal remain constant, but as the amplitude of the information signal changes, so the frequency of the carrier would changes correspondingly. So in this case, the higher the modulating, the higher the frequency it is. It's very dense, okay? At the part that we have the higher amplitude. So that is for frequency modulation FM, okay? But the allocation is the same method that is used in AM. Only that the value would be different. FM band start from 88 to 108 megahertz. Okay. Whereas for the phase modulation, it's modulated following the changing of the amplitude of the modulating signal. So the peak amplitude and frequency carrier signal remain constant. So frequency remains the constant, but as the amplitude of the information signal change, okay, there's a changes on the amplitude. So the phase of that carrier would changes accordingly. As you can see here, the number of phase, okay, the number of the phase here would be different based on the peak amplitude and the frequencies, changing amplitude of the signals audio. Alright. So okay, so that's it for the chapter 1. Chapter 2 actually. So I have covered for chapter physical, data signals and transmission mode. Okay, so that's the last part. Okay, I promised that I want to give you an assignment, but I need to give you time for you to do some exercise. Okay, we are using a Wireshark. So my assignment here, it's a group assignment because you need to present it. Okay, so at the moment, I was thinking that you can use a PowerPoint. And then let's say, it requires that you need to present it. Then we would use the video presentation. Okay, so that's for the backup. That's for the backup only. Okay, in any case, I would ask you to present it face to face, not face to face. Online. Okay. Now, this is a preliminary because I need feedback from you if you don't understand anything. Okay. So, I forgot about this part. So this one, it's the last chapter 1. Because of the future trends in our data communication. I forgot about it. Okay, my mistake. Sorry. Okay. So, what is the future trends in the data communications? Because of the changes of the technology that we have, it affects, okay, the method of how in our daily life. Because of we have the wireless LAN, okay, then the method of operations, okay, lean to, okay, going through the bring your own device. So there's a growth of mobile devices, and there's a BYOD policies. So there's a benefits, but also the security challenges, because anything from outside, okay, bring outside can bring security vulnerabilities, okay. And then the current trends, okay, have the emerged that there's an internet of things. So there's a integration of objects with the internet, such as smart appliances and autonomous vehicles. Okay, so there's a lot of thing. Anything can be assigned with an IP address and something else. Okay, and then education, everything is online. So the expansion beyond gaming to education, politics, activism, like example like MOOC and online political campaign, can be done online. So what are the implications? The network and internet changes, because of the ease of information changes, would introduce some risk in the cyber security. And then the device connectivity raise some issues of in the security risk from the bring your own device and the IoT, because it's not in stable, right? In stable stages. Is because of they still did not solve yet the security risk. And then in this case, they want to balance between the benefits and risks. And then because we have the cloud computing, so they introduce the secure storage and data transfer. So there's an increasing need for a secure storage solutions and data transfer method using the cloud computing as a solution. So this is the changes happen in the current life, in the our current age. So that's the last part for the chapter 1. Forgot to tell you. Okay, so let's discuss for the assignment. So, please choose the following type of application, or you may suggest other application type. So, this is regarding the application, the protocol that is related to the application that you select. So, we have email, file transfer, online shopping, video streaming, VoIP, VPN, DHCP, client server interactions, and also telnet. Um, you may also suggest other application that the example is from your own workplace, also can. Okay. Now the description, the what do you need to do is that you need to discuss how the messages are transferred using layers and the different protocols or PDUs used at each layer. So in this case, I want you to see the different PDUs in the messages that you send using Wireshark. I would give you an exercises that you may use, okay, that for you to understand, and also notes, okay, Wireshark quiz start guide, how to examine to capture it. So you need to install first, and then start to capture. Okay, so here when I start to capture, okay, so now I will continue without saving. So there's an increased number of packets here. Okay, I want you to capture based on the type of application that you use. At the moment, what I've opened is my Teams, right? Okay, so I need to select and filter, because one of them is my web browser, and sometimes I'm opening my what is it, WhatsApp, the online chat, so you need to differentiate it, which one is the application related to the one that the topic that you select. So and then I stop it, and then I will need to filter it, right? So when you filter it, you need to examine the content of the packets, okay, and explain, okay, what happened at this time when you select this. Okay, when you select it, this one, when you select this, you should be able to see the data, the sessions, the user datagram. Okay, in this case, what happened? So there's an IP here with the destination, and then so this one is on the level 3, yeah, layer 3. So this is what happened, and then this is the content inside the frame. But if you want to understand it, you may also use statistic and then the flow graph. Here it shows that the channel data turn message that is happening on this level. Okay. And then there's a receiver report and everything else. Because I'm using teleconferencing, so they are using RTCP. Okay, so that's related to the protocol of that applications that you are using. So I need to you need to identify which protocol is used for for your application that you choose. Okay, so you may use this flow graph here to explain about the process after you filter it. After you filter it. Okay, now let's go back to the questions back again. Now once you have captured it, then you need to filter based on the selected application protocol. Let's say if you use email applications, then you must filter only for your email application only. Okay, but during the capture, you must do some action. For example, if it's email, you need to read or send emails during the demonstration, and then explain the process. Okay, explain the process. For this description, think of it as a conversation. So, for example, two of the frames will contain DNS requests for an IP address for the website, and then the DNS answer with the IP number. So, in this case, you elaborate it like a conversation, like a story. Okay, so in order for you to access or to request a web browser or a web server pages, then first, we need to DNS request for an IP address, and then reply back again with the IP address, get the reply of the DNS with the IP address of the server, web server itself. Then you elaborate more the next frame that is related to the process in your application. Okay, then present it using a PowerPoint presentation and demonstrate, explain it, the process, based on this, okay, your application. So you can do this in 2 to 3 person. I did not create yet the topic here. Okay, once I have create the choice, the choice for the application type, then I would inform it to you later. Okay. So, is there any question regarding the application? Is there any question regarding the application? Sorry, the assignment. Sorry. Is there any question?
No, doctor.
No? Also means that you understand, what do you need to do? So what I want to see is your understanding on the packet captured by the Wireshark. Okay? So inside the video or inside the presentation, you may use the screenshot of the Wireshark, okay, of the Wireshark that you have captured, and then you label it or you emphasis in which part that you want to explain more. Okay, so that's it. All right. Sorry for the extended time. It's because of it's supposed to be 3 hours for our lecture. Okay, but because we have a break at the time, so I have extended to 9:30. Okay, sorry about that. Inshallah, because I have managed successfully to finish the chapters for this chapter 2, hopefully the time would be shortened next week. Oh, I forgot. Next week is Deepavali, right? So it will not be synchronous. Is that okay? Or is that okay? I would upload the video lecture, the recorded lecture. Okay? All right. Okay, that's it. Happy holiday for the next week, and then I'll see you after the holiday. Okay? So that's all. Thank you.
Thank you, madam.
Okay, you're welcome.
Thank you, madam.
Happy Deepavali to everyone. Bye. Happy holidays.
Happy holiday. Okay.
Thank you, Rada.
Okay, you're welcome. You're welcome. You're welcome.